Hello everyone, welcome back to Math with Allison. Today we're working in our sequences and series, so we're going to be talking about how we can represent functions as power series. So let's go ahead and dive into it. We are going to begin with a generic power series here. We have the summation n equals 0 to infinity of x to the power of n. So what this looks like is 1 plus x squared plus x cubed all the way, so on and so forth. But for this one, we're going to work with x values less than 1. So let's go ahead and think about this. This is a special type of series, and it's actually a geometric series, right? If we were to replace x with like 1/2, we would have 1 over 2 to the power of n. Here we would have a geometric series, right? In this case, we have that our common ratio r is just going to be equal to x, which is why we have to have x values less than 1. So in this case, we have a, the initial value, is equal to 1, and our common ratio r is equal to x. So since x is absolutely less than 1, we know that the series is going to converge, right? That's the rules of a geometric series. So let's go ahead and see what it converges to. So I know generically it converges to a over 1 minus r. So let's go ahead and plug in what we know. We know a is equal to 1, so 1 over 1 minus x. And this right here is a function of x. So here we have a function of x represented as a power series. So here, let's go ahead and talk about what that looks like. Now let's see what this looks like with Desmos to better understand how we can represent a function. So we have 1 divided by 1 minus x. So here is our function, right? And we're working just with x values between -1 and 1. So it's just going to be this part of the function. So here we're representing this with the power series. So first we start with 1. This does not accurately describe our function quite yet, but here we add x. Here we're getting a little closer, so plus x squared, right? That's getting a little better, plus, and we're going to go add x cubed. Now notice that we're getting closer and closer to what the actual function is. So let's say plus x to the power of 4. Now we're getting real close, plus, and this would keep going forever, x to the power of 5. And so as you can see, the more we add to this series, the more accurate it is going to describe our actual function. So now we're going to go ahead and use this. We want to express 1 over 1 plus x squared as a power series. So what we're going to do is use the fact that 1 over 1 minus x is equal to the summation n equals 0 to infinity of, and that's just x to the power of n. We want to go ahead and change our function so it looks something of this form. So here we have 1 over 1 plus x squared. The first thing I want is to have 1 minus. So what I can do is I can subtract a negative. So 1 plus x squared is equivalent to 1 minus negative x squared. Now here what we're doing is we're going to replace x in our series. So instead of just having a normal x, what we're going to replace it with is negative x squared. So this is equal to the summation n equals 0 to infinity of, and that's going to be negative x squared to the power of n. So I just replaced it like you would in a function, f of x versus f of x squared, right? So here what we could do next is we could try to simplify this a little bit. Summation n equals 0 to infinity. We're going to have that -1 to the power of n, right? That's the negative. And then we have x squared to the power of n, or we can just multiply the exponents together. So x to the 2n. So if we were to write this out, right, if we plug in n equals 0, we get 1 minus x squared plus x to the power of 4 minus x6 plus so on and so forth. And remember though, in order for this to actually converge, we need that the common ratio has to be less than 1. So in our case, we have to have negative x squared be less than 1, or we can just write that, right? It doesn't matter with the absolute signs if that negative is there or not. So here, this is going to converge, right? This is going to be equal to this series for all x squared less than 1. So in general, what does this look like, right? We have 1 over 1 minus some kind of function f of x is equal to, we got the summation n equals 0 to infinity, and you just plug in that function to the power of n. And remember, we're working with a geometric series, so we need that common ratio f of x has to be absolutely less than 1. So let's go ahead and try this again. We want to find a power series for 1 over x plus 2, and we also want to find its interval of convergence. So let's go ahead and use the fact that we know that 1 over 1 minus x is equal to the summation x to the n. Now what I want to do is I want to manipulate 1 over x plus 2 to look something of that form. The first thing I'm going to do is just switch the order. So 2 plus x. So we need this 2 to be equal to 1. How do we do that? We pull out a 2 in the denominator. So here we get 1 plus, and that's going to be x divided by 2. Now we're super close, right? We have a scalar 1/2 times 1 over 1. And now I don't want a plus, I want a minus. So I'm going to subtract a negative. 1 minus negative x over 2. So now I have something that I can plug into the summation. So this is going to be 1/2 times, and that's going to be the summation, n equals 0 to infinity, negative x over 2 to the power of n. Now we can go ahead and simplify this if you wanted to. So 1/2, we have the summation, n equals 0 to infinity. Here we have negative 1 to the power of n, x to the n over 2 to the n. Notice here that we can actually combine like terms because we have a 1/2 out front and we have 2 to the n in the denominator. So you could rewrite this as a summation, n equals 0 to infinity. We have that negative 1 to the n, x to the n, but then that becomes 2n plus 1, right? You're just adding their exponents together. So that's how we can represent our function as a power series. And be careful again because we're working with a geometric series. So I want our common ratio, so that's going to be negative x over 2 to be less than 1. Really, this is the same as x over 2 has to be less than 1, and you can multiply both sides by 2 in order to get x all by itself. So we have the absolute value of x must be less than 2. So right now we're working with an interval of convergence from negative 2 to positive 2. Remember, you also have to check if the endpoints are going to be inside that interval, right? Maybe it converges at an endpoint. So let's go ahead and try plugging in a value. Let's just plug in x equals negative 2 first. Here we have the summation, n equals 0 to infinity, negative 1 to the n, and that becomes negative 2 to the n divided by 2n plus 1. So here we can rewrite this, right? We're going to go ahead and simplify the values in here. Negative 1 to the n, negative 1 to the n, 2 to the n over 2 to the n plus 1. So here, notice what cancels. First of all, negative 1 times negative 1 is always going to be equal to positive 1. And then here we have 2 to the n can cancel out with one of the 2 to the n's in the denominator, right? And that just leaves a 2 in the denominator. So this is equal to the summation, n equals 0 to infinity, and that's just going to be a 1/2. So what is a summation of 1/2? Well, it just means that we are adding together 1/2 forever and forever. So if you think about it in terms of diverging or converging, this is going to diverge because we are forever adding 1/2. So at x equals negative 2, we're not going to include that endpoint because it diverges. And actually, if you were to plug in x equals 2, you would have a similar process. If you go through, plug it in, simplify it down, you would also find that it diverges. So if you want to try that on your own, you're totally welcome to. But here we have the interval of convergence for this power series is going to be from negative 2 up to 2. We're not going to include those endpoints. So here we have some generic functions that can be written as power series. And actually you can prove these with Taylor series, but we're not quite there yet. But here you have just generic ones. We have sine of x, cosine of x, e to the x, and then natural log of 1 plus x for x values between negative 1 and 1. And then same thing with the one that we just learned, right, with the geometric series, 1 over 1 minus x. So here you can use these. We will also develop them in a later video if you want to understand them a bit deeper. But there are other types of questions that can be asked when we're trying to represent functions with power series. We just had 2 questions where we had to write it out as power series, but sometimes it can be backwards, right? We're going to be given a power series and we want to go ahead and find the function that it represents. So here's an example. We have x to the power of 6 plus x to the power of 7 plus blah, blah, blah. So we want to go ahead and write this as a function. So how are we going to do that? We need to recognize what this is super close to. So notice that 1 over 1 minus x is equal to 1 plus x squared plus x cubed, so on and so forth. It's super close to this series. The only thing is that we're starting at x to the power of 6. So what if I multiply both sides by x to the power of 6? Here we get x to the power of 6 over 1 minus x is equal to, and if we multiply that in, we get x to the power of 6 plus x to the power of 7 plus x to the power of 8, and then, we're going so on and so forth. So here what we did was we found our function that represents that power series, right? X to the power of 6 over 1 minus x. So remember though, this is a geometric series, so we need that common ratio to be less than 1, right? So this is going to be 4 x values between -1 and 1. Another way that this question can be asked is instead of the written out power series, you might have the summation notation, and you might want to write that as a function. So let's go ahead and try to do this thing. Here we have the summation, n equals 0 to infinity. I'm just going to rewrite it. Let's work backwards. So let's try to combine everything all to the power of n, right? Because each of these things are raised to the power of n. So the summation n equals 0 to infinity, that's going to be -1 times x, so I'm just going to write that as -x divided by 3 to the power of n. And remember what we have. This is like our little function here. We have -x divided by 3 is our function. That's going to be our common ratio, so we know it needs to be less than 1. And we have this is going to be equal to, that's going to be 1 over 1 minus, and plug it in, -x divided by 3. So this is equal to 1 over, that's going to be 1 plus x over 3. And if you wanted to, you can multiply the numerator and the denominator by 3. So we get 3 over 3 plus x. So this right here is our function. Let's go ahead and find which x values this is true for, right? So this is the same as x divided by 3 is less than 1. Multiply both sides by 3. We get the absolute value of x has to be less than 3. So this is going to be for values in between -3 and 3. So that's how we can write out functions as power series. It's a bit more interesting with Taylor series, but this is just a bit of an introduction for it. If you enjoyed this video, I have many more like it, so make sure to check out my playlists. They're linked down below. Otherwise, please give this video a thumbs up and comment any topics you'd like to see done. Thanks for watching.